Okay, with enthalpy of formation, the degree symbol tells us that the reaction of formation has taken place under standard conditions. So I'm going to give you those standard conditions on the next slide. But heat of formation or enthalpy of formation is how much energy it takes to form individual compounds. With enthalpy of reaction that we've looked at so far, it tells us how much heat or enthalpy change there was for that particular reaction. And now we're going to be able to kind of get to that heat of reaction or enthalpy of reaction point from the enthalpy of formation point. So that's a lot of talking for what's going to require essentially not as much effort as Hess's law. The important thing to understand is that for enthalpy of formation, it is given always for 1 mole of the substance. So in Hess's law, we weren't concerned if our reactants or our products had more than 1 mole in our chemical formula. But now we're concerned with the mole ratios in the problem. So all of the heat of formations given to us, and there's going to be a big table in the back of our textbook that we're going to use a lot. All of those are given to us based on 1 mole of that product forming. And so we're going to manipulate those numbers based on the reaction that we're given. So a lot of introduction there. I'm going to tell you what standard states mean. So if it says it's given under standard states, it's got a certain temperature and pressure. Certain temperature and pressure conditions it's got to be under in order to be a standard state. So for a compound, the gas is exactly 1 atmosphere. For a solution, it's exactly 1 molar. And if it's a pure substance, it's got to be in a liquid or a solid state. Okay, we are not going to deal with right now things that are not at these standard states. So the fact that you know the values for them is not a huge deal. But I just think it's okay for you to have the definition that goes with that. So a standard state means we're at 1 atmosphere of pressure, 1 molar concentration in our solution, and our pure substance has to be liquid or solid. If we're dealing with an individual element, then the state of the element, liquid, solid, or gas, is whatever state it is at those conditions, 1 atmosphere, 25 degrees Celsius. Yeah, sorry. Okay, so I gave you a lot of introduction for heat of formation, but solving for heat of formation is not near as complex as it really sounds. We're going to deal with things that are always at standard state, so we don't really care what these values are. We just need to know that it's at standard state. Things that we do need to look for enthalpies of formation is that we got to look at mole ratio, and we have to look at states in our chemical reaction. It makes a difference if we're looking at liquid water or gaseous water, water vapor, right? It makes a difference if we're looking at liquid or solid or whatever it happens to be. So we're going to go ahead and dive into one here. We're going to calculate the enthalpy of formation or the delta H change for this chemical reaction. So go ahead and get this reaction written down. CH4 gas. I'm going to write it a little bit bigger underneath here so we have more room. CH4. It is important here to put the states. Plus 2O2 yields CO2 plus 2H2O liquid. So to calculate our enthalpy of formation, we don't have mini reactions like we did with enthalpy of reaction, right? We don't have mini reactions, but we do have this huge database in the back of our book that tells us how much heat was required to form CH4, and how much heat was required to form O2, and how much heat was required to form each of our individual compounds. And so if you look in the back of your book on it really starts on A19, but A20 is the page that you're really going to want. It's way in the back. It's appendix number 4, but it's on page A20. So it's like just before we get to the answers in the back of the book. Okay, A19 is really where it starts, but A20 is going to where we be. A20 and 21 are going to be where we find a majority of our data. So what we have to do is we need to find what's the enthalpy of formation for each of our individual compounds, CH4 and O2 and CO2 and water, right? We need to find what is the enthalpy of formation for each of those things. Okay, so let's look at CH4 in our book, right? They're organized by element. So CH4 is a carbon molecule. So CH4, and you see how it has a G there? That means that it's particular for the gaseous state. So we look over and we want to find delta HF. So that's the first column of data. So what is our value? Negative 75. So I just like to list that basically right underneath there. Okay, there's lots of ways you can do this. Your book does not show you to do it this way, but this is how I find it easiest. For O2, let's find O2. What's O2 gas? 0. And you'll see that, okay, let's look at H2 just for fun. H2 gas is what? Just for fun. It's not in our compound. 0. So any elemental, anything that's elemental and it's in its natural state is 0. Okay, so oxygen gas, hydrogen gas, nitrogen gas, right? Anything standard state that's purely elemental would be a 0 heat of formation. Okay, so that's a 0.
Heat of formation of an element is always 0.
Heat of the formation of an elemental in its standard state is 0, but I would always check your book just to make sure, right? While you're already back here, just check it. Okay, CO2 gives us what? Negative 393.5. And then H2O gives us negative 286. So here's what we do. We're going to add them all together just like we did with Hess's law. Except we have to reverse things because these are all heat of formation. These are heat of formation. So in this formula, is CH4 being formed or is it the reactant? In this reaction, is CH4 a product like it was formed or is it a reactant? Reactant. So we're going to have to reverse the sign for CH4 because the negative 75 is based on it being formed, right? It's based on CH4 being a product, but it's not a product in this example. It's a reactant. And then how many moles of CH4 do we have? No, not 0. We just have 1. So we don't have to multiply it by anything. We do need to reverse the sign. So really we need a plus 75 there.
Wait, does it go product reactant?
Always goes reactants, products, but in the heat of formation, it's assuming that CH4 is a product. So that's where the negative 75. Negative 75 would be true if it were a product, but it's not. It's a reactant in this formula, or in this equation. Okay, what about CO2? Is it a reactant or a product? Product. So we can keep it. Keep negative 393. Do we need to multiply it by anything? No, CO2 is a product. Everything on the right side is a product. Everything on the left side is a reactant.
So when you reverse them, then you could just pick whichever one you need to. You don't have to reverse the whole thing.
You don't have to reverse the whole thing. So we're doing basically the work we do with mini reactions, but without having to draw out the mini reactions.
Okay.
Kind of. Okay, so CH4 has a mini reaction that goes with it. It would say carbon plus H2 yields CH4, right? It would say C plus 2H2 yields CH4. But we don't have to write out the mini reaction. Right, with heat of formation, it gives us all these data tables that tells us if CH4 is the product, it takes negative 75 joules. Okay? On the last one, is H2O a product or a reactant? It's a product, so we keep the sign, but what do we need to do? Multiply it by 2 because that 286 is based on 1 mole of water being formed, but in ours we have 2 moles being formed. So we take that times 2, 286. So negative 572. So that means we need to add these all together. Plus 75, negative 393, negative 572.
Wait, you add all of them together?
Yep, you add all of them together. We reversed our sign on the 75 because CH4 is not a product, it's a reactant.
So you can just reverse it no matter of just one element?
Yes, you just can reverse one. You wouldn't ever reverse the ones on the product side because they're a product. But the reactant side you might have to reverse.
So, but why did you reverse it?
Okay, because the negative 75 value that we found in the book, that is only true when CH4 is a product. So what it looks like is we would have a mini reaction like this. C plus 2H2 yields CH4. And that would have a delta H, a formation of negative 75. Right? But if we were doing like we do with Hess's law and we reversed our reaction, that would reverse the sign of that. So we're doing the work of the manipulation, but we don't have to write out all these mini reactions.
So are all of these for the product then?
All of these are for those as products. Yes. Does that make sense?
Yeah.
All the data in the back of the book assumes that those formulas are products. So I think we get, let's see, I haven't added it up yet. What do we get? Negative 890.5. So negative 890.5. Is it joules or kilojoules? Kilojoules. Calculate delta H formation for this reaction. Except here it gave you all the values. You didn't even have to look in your textbook. Okay?
But this still means that they're for the product.
It still means that those are true if they're products. So if they're not products in the original reaction, you have to reverse them. Okay, so sodium we know is 0. H2O we know is negative 286. NaOH we know is negative 470. And H2 we know is 0. Okay, what do we need to do with sodium? We would multiply that by 2, but it's a 0, so there's not really a reason to do that. For water, what do we need to do? We need to reverse, and we need to multiply by 2. We reverse it because in our reaction, it's a reactant. So we reverse 286 times 2, and that gives me positive 572. Right, what do we need to do with sodium hydroxide? Multiply by 2. Do we need to reverse that one?
No.
No, because it's already a product. So negative 940. So we get negative 368. Yes? No? Maybe? We're feeling pretty good about that?
Yeah.
Okay. We can do this one. We can do this. Okay, then that's it. That's it. That's it.